Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello everybody and welcome to today's episode of the Space Industry Podcast by satsearch. I'm joined today by two returning guests, Michael and Adrian from global electronics manufacturer Texas Instruments. And today we're going to be talking a little bit about packaging innovations for space applications. A very interesting topic, a topic we've touched on before in conversations with Texas Instruments, but it's very important for missions at all levels, subsystem manufacturers, everybody to understand that the performance you're able to get from your technology is related obviously to the performance that the fundamental components are able to deliver, and packaging is a key part of that. So Michael, Adrian, hello, welcome, and thank you very much for being here on the podcast today. Great to have you both. Let's get straight into the conversation now. Before we take a deep dive into the topic, I wondered if you could tell us briefly about packaging innovations for space applications and why are these particularly important perhaps for the new space industry?
Let me start with maybe a little bit explanation about what does it mean traditional space packages. And what the industry is actually using for a very long time are those ceramic hermetically sealed packages, right? But those packages, they have several challenges. And one of them is, for example, those require so-called forming and trimming of the pins. And that's normally not done at the customers directly. Those are third parties involved in that process. And also in total, if you look at those components, those are very big and also heavy components, which obviously leads to costs. And now, if we look at the innovations in terms of packages, if you look at the traditional ceramic packages, the material used in those packages could be very challenging for some of the application. And I'm thinking here about parasitics involved in the package construction that could be challenging, for example, for your RF application or power management. And now, if you compare this to the plastic package, you immediately see that, for example, bond wires are much shorter. And also, in case of BGA packages, there are almost no bond wires. So you reduce immediately your inductance, capacitance, and resistance in your package. Also, for a process of manufacturing of your ceramic packages, there is a so-called heat resistance alloy needed, which is high resistance. And if we look at the plastic packages, you can use more modern materials like aluminum or gold, which is helping you lowering the resistance. So all those points are really playing a role and giving you advantage in applications like RF or power management. Now, another perspective is the integration. So we also innovate in the field of integration. And I'm thinking here especially about multi-chip integration, because this requires also innovation in package technology. Or if you look at the power management solution, where the power density increase with every upcoming version of the product, you also need to think about how to dissipate the power or the heat from your device. So you need to innovate on heat pad construction, for example. And then if we look at this more space specific, when working in space applications, there are really different requirements you need to consider, like material used for your package construction. That's very important. Or requirements in terms of vibration or soldering. That's also something customer needs to consider when using new packages. So all those requirements needs to be considered when talking about innovation in packages. And Texas Instruments played really a major role in supporting the standardization of this new QML Class P standard, which is using plastic. But to be very clear on this, we will not stop designing ceramic packages and bringing also ceramic devices into the market. That's only an extension of our existing portfolio.
No, that makes sense. As you say, these are legacy components in some areas, and it's important that they can continue to be supported and created. And as with everything in space, there's a trade-off. So the more options available makes sense. And yeah, it's very interesting you highlighted the increased power requirements and therefore the heat requirements that need to be dissipated in upcoming missions, because we're seeing this everywhere with satellites becoming more and more powerful, edge computing, onboard processing, and larger systems more powerful, Earth observation payloads, etc. They're not to mention in orbit applications, which are going to require really high power and all sorts of other resources in order to carry out the applications that people are trying to build in space. But yeah, really interesting. Makes a lot of sense. Thank you for laying it out like that. So I wondered, I think if I could ask Michael next then, if you could explain the fundamental advantages of using plastic packages rather than ceramics in space applications, and if you could relate these advances in the technology to advances in the industry, to differences we're seeing in the industry as well.
Yeah, happy to do so. I think the very first one is the obvious one. Size, weight, power, and cost are the fundamental requirements in space. That's everywhere the same. If you look at size, it's self-explanatory. The devices are much, much smaller by themselves. Then further, these smaller dimensions help you then also to reduce the parasitics, as we call them, the parasitic capacitance, inductance, and resistance of all these leads and bond wires. That leads directly to a better performance for RF devices or higher bandwidth, and also much better performance for power supply designs, where it all goes hand in hand, efficiency and switching frequencies, and give you their big leg up. The second key advantage that Adrian mentioned already is the easier use of the components. There's no forming and trimming is required. And there's always this quality concern that you have to give many times these forming and trim components out of house or even in-house to another division. And of course, things can happen, right? If you touch them, they can be damaged, and then you need to order new ones, and you may have a delay in your development or even in your launch date. So that goes away, makes it much, much easier. The third one, also a very significant advantage, is this pin compatibility that's now possible between different quality classes, right? We have QMLP has also a class 1 mission targeting quality class, but we have also the red tolerant level, like our space enhanced products that TI offers there, targeting more the LEO constellations. But they can be now in the very same layout, same pin out, and you have one R&D investment and you use it for different mission profiles. And last not least, right, I think you mentioned it already, higher digital processing capabilities. Thanks to these newer, bigger packages, or bigger in terms of number of pins, right? You look at pin grid array or ball grid array, you have really hundreds of pins available. And that is required for anything that is a high performance digital processing chip. You need a larger memory interface. You have all kind of interfaces that go in there. And that having now these digital processing devices available allows us to do in-orbit decision making and allows us to for data compression or edge computing, these things. All those things help us to reduce the data traffic forward and backward to Earth. And that is a saving in complexity, of course, but also everything you transmit requires power. The less you transmit in data, the less power you need for that one. So that's also a big advantage there. And another saving comes from the smart routing from satellite to satellite. So you have multiple passes, and you can now work around any congestion, or you have any bad weather conditions where it's maybe difficult to reach a ground station. That can be smart routed from satellite to satellite, and even enables our backbone applications like what the EU is planning for the IRIS-2 constellation.
Maybe I can also add to that, because it's really like this QML standard exists with its many classes really to ensure the predictability in design, and also to meet all the qualification and certification which is required for governmental standard. But now with this QML class P standard, this is really something which allow our customers to use radiation hardened plastic package, and this can be used, as Michael mentioned, for different kind of application like power management, processor, communication, high speed data acquisition in your satellite or spacecraft.
Interesting. Yeah, a focus on standards is something we have discussed a number of times on the podcast, and it's really good to see these being led, from the ground up, if you don't mind me saying, when led by the industry, by the suppliers in the industry, as well as through engagement with the government bodies and the international organizations that oversee these sorts of things. But standards are only going to be useful if they're actually capable of being deployed and easy to deploy. And so it's really good that you guys are engaging in that discussion. And yeah, thank you, Michael, for explaining the relationship between plastic packaging and the industry applications. We use the analogy of satellites being like computers quite a lot, and building a more efficient computer doesn't just mean that you, as you covered, doesn't just mean that you can carry out the applications on that computer faster, with less power, with less heat produced and more easily, blah, blah, blah. It also means you can create new applications by combining computers together, which you covered. And I think that's really interesting for people to think about and to understand. And it's based on the performance of the components that are used to create that computer, that satellite. So just to follow up from there a little bit, could you explain a bit more how smaller dimensions in the packaging and in the innovations in the packaging can lead to advantages in the SWaP budget, the size, weight, power, SWaP+C, size, weight, power, and cost, of course, and what specific areas, advancements or applications would benefit the most from this, or can benefit the most from this?
Yeah, happy to dive a little bit deeper into it. So when these reduced parasitics, as we call it, right? So the way we need to look at this is like you look at the fairly small die inside the package, and then you have to bring out the pins from the die out to those leads you can solder actually on the board. And in between is your lead frame and your bonding wires. And if you look at those things as a little piece of wire, you have to look at this wire that, even if it's small, it still adds a little bit of capacitance and a little bit of resistance. And of course, every extra millimeter adds more of these R, L, and C parasitic impedances. Now, if you're able now in the other direction reduce these parasitic inductance, capacitance, and resistance, that allows you to go to higher frequencies, which then in turn your applications that benefit a lot from that are primarily RF applications, where you get now even into even higher gigahertz areas and even more bandwidth, and higher switching frequencies do also help powered supplies very much, because the higher your switching frequency there is, the lower or the smaller your transformers and your capacitors can go. And that is, of course, only possible if your switching losses are not too high. And that is where these smaller distances or smaller dimensions really help you a lot to get the losses in the switching down. And an extra one that's also not so obvious, Adrian indicated already, right? In these ceramic packages, they need to be cured at a fairly high temperature. The ceramic itself needs to be cured. And therefore, but it has been cured while everything is already inside the package, including our bond wires and lead frames. And they have to be therefore be made out of a heat-resistant alloy. But such alloys have higher resistance than gold or aluminum, what we ideally love to use in such packages. And only these newer plastic packages allow us really to use gold or aluminum and have this lower resistance. And that is important. With all those switching losses and all these resistance reductances, we save power. And saving power in space is always a double benefit. First of all, the power you don't use, you don't have to generate. That's a direct cost saver. But in space, we have such problems in getting rid of the heat afterwards. And heat dissipation is an effort itself. So first not generating and then later on not having to dissipate it is a double benefit from it. And of course, if you look at the smaller sizes, be it because of the smaller packages, the smaller overall discrete components you use, like the transformer or capacitors, everything that reduces your PCB size, reduces weight, and reduces the cost ultimately.
Thank you. Yeah, that makes absolute sense. Covered all the points there, reducing size, weight, and power. Obviously reduces cost, and simplifying, as well as simplifying the engineering, reduces cost. So thank you. I think so important point that reduction in power is a double benefit. And even when we're seeing larger satellites being created where heat dissipation is less of a problem, it is obviously in the interests of those mission designers to pack in as much useful technology as they can, which can ramp things up again. And then all of a sudden your larger form factor satellite, which maybe was created because there were cost savings that you got probably due to the fundamental aperture of the Earth observation, but you think, we get cost savings in reduction in heat, etc. But only if you maximize the potential of that system and the space that you do have. So the way you've laid this out, I think, really clearly explains how that can be done by considering the packaging of the components. Thank you. Now, one thing I wanted to ask about as well that was mentioned earlier is the manufacturing process. You covered that the ease with which plastic packages can be created due to the absence of the forming or trimming of the frames, and how this can mean that you don't need to send components out to third parties or other departments, and the potential of delays and something going wrong in transit or when it's being used by different teams. So could you go a bit deeper into how this simplification impacts the manufacturing process and then the result, the overall efficiency in space applications too?
Yes, sure. So, as you mentioned, this is really something which is very time consuming because that's the challenge. The customer needs to form and trim the pins of the package. And as I mentioned already, this is normally not done in-house. There are only specific third parties which are really experts in doing this. Those third parties are involved in that process. This means for the customer, they need to give out the parts out of their hands and really trust the third party that they will handle the parts correctly. And as I mentioned, that's a really huge time factor because then it's out of your control, right? You need to wait for the third party to complete the process, and you need to trust they will do everything correctly. And there is also a risk involved. Something can go wrong with the trimming and forming, and parts can be broken or something like that. You will be forced to reorder those parts and wait again. So it's really time-consuming process. And another point here is the qualification of ceramic packages. Those ceramic packages needs to be accepted by the manufacturing side, and this requires the package qualification. And if you now look at the plastic packages, this process of qualifying packages is much shorter. And if we even look from our side, from the manufacturer side at this, really the plastic packages, those are providing us much more flexibility in investing in much broader portfolios. So we can simply bring more parts into the market. And we can benefit from experience we already have from different markets, like automotive, for example. This means for us really less risk by designing new parts and bringing them into the market.
Brilliant. That's always going to be benefit, I think, to both suppliers and the customers in the market. It makes absolute sense to me. I think as much as at satsearch we deal with people at all levels of the supply chain who are purchasing and moving equipment and technologies from one place to the other, mission designers like to have control of things in-house. So it makes a lot of sense to be able to do that. And where you do have to send things out, the customization, qualification, whatever it is, then enabling that process on a shorter timescale as possible and with as much reliability as possible, I think is brilliant. So thank you, Adrian. That's great. Now, another thing that was highlighted is the pin compatibility between quality classes and how this enables you to reuse and benefit from R&D investments multiple times. So and this was covered earlier. I wondered if you could share some examples of where the pin compatibility has been a particular advantage, or has resulted in and the development of something that has helped move the mission or the technology on a lot further, which wouldn't have been maybe possible, or at least as easy, if that pin compatibility wasn't there.
Yeah, I think the way we should look at this is really from the mission profile perspective. So each mission has its own profile, as we call it, for a different radiation hardness level that it requires. Because each mission is either it goes for the geostationary orbit or the low Earth orbit. There are different times they have to be in space, maybe just 3 years, maybe up to 15 years. Then the PCB we're talking about, or the electronic group we're talking about, might be inside the satellite and fairly well shielded. Others might be more on the outer side and not that well shielded. And then overall, we had a certain criticality level of your mission itself. It can be a pretty experimental mission, but there are other missions where really the nation's reputation depends on it, and really nothing must go wrong. Totally unthinkable that something wouldn't work out. And there is where ultimately, if you're a designer, you design, of course, your design to the best performance. But if different missions come along and you want to reuse your design, you need to be, or ideally, you can reuse what you have done before and apply, thanks to different components you're mounting now on, reuse that design and be also much faster in your execution and much lower in on the schedule risk, right? Because you ultimately know what you're doing. You're just swapping components in and out according to the mission profile requirements. And the next advantage is, of course, in this industry, we very much look also into flight heritage and maturity of designs. And if there is already a lot of flight heritage, we like this design even more and know that this component is probably more reliable than other things that are fairly new. Now, if you're able to supply not only one mission, you're able to supply a lot of mission and different motion profiles. That also accumulates much faster to a certain level of flight heritage, as you're way more flying into space than other designs. And yeah, having more missions in parallel running or more business you accumulate there, that also enables a higher purchasing volume and manufacturing volumes. You benefit from the classic economies of scale. You have a better negotiation position for the higher volumes, and it's also easier in your inventory and supply chain management. So there's big use in reusing your R&D investment and maximize return of investment there. Now, the other thing when you look at this is if QMLP, the radiation hard and class 1 new standard, and our radiation tolerant class, the space enhanced products, SEP, they come in the same package and the same form factor. That enables a really 100% same performance. And allowing and making sure you have no change in form factor is really a huge important factor, especially when you look at power designs or RF designs. Each time you change the form factor there, you will have a new optimization effort ahead of you. And one thing is also clear, if your packages are larger, you will always have lower performance in these RF and power applications. And then you have, for different mission profiles, you have different performance levels. I think this is also very hard to market that product properly. Otherwise, it's just one that fits it all and makes it the story very straightforward. All that being said, all these new advances, I want to probably also point out, right, where we are with QMLP and also space enhanced products. These are fairly new to the space market, and it's not like we have the whole box full of all parts and everything is available in each flavor, but we're working towards this and we're highly encouraged. We have very positive feedback from our customers on this, and you can be assured that we will now execute and continue bringing out a lot of QMLP and space enhanced product flavors out there, and all in addition to QMLV, of course.
Brilliant, thank you. That's very clear. We've had a lot of conversations with both suppliers and end users or people interested in designing missions who have experience of other industries and see space as a single operating environment. But really, as you've mentioned, the environment in low Earth orbit is very different to GEO. And if you want to then look at cislunar or lunar and even the Martian environment, which a lot of these applications and exploration missions are talking about doing, at least in these big, the big moonshot projects and companies who have big ideas for the future. They need to understand that these are very different operating environments. But if you can develop technologies that can be used in all of them, or at least on comparable timescales or timescales that are useful enough to get some benefit out of it, you're only going to benefit from, as you've mentioned, the economies of scale, the simpler inventory management, negotiation, the ability to market and create products, bring products to market that have multiple applications and uses in a cohesive story. So I think this is, and relating that back to the fundamental performance of the electronic components in them, I think is a really interesting message. So thank you for that. And you finished by discussing, in that answer, you finished by discussing the QMLP standard, and we touched on this earlier. And as I mentioned, I really believe that the standardization requirements right across the space supply chain is a very important area. So I wondered if you could talk a little bit more about how the role that Texas Instruments is playing or has played in the QMLP standard, and why the standard is important and is influencing the industry's approach to packaging technologies.
Yeah, sure. So if you think about this, and we were talking about all those challenges we have with ceramic packages. If you think about this, the need for having a plastic package was always there. And different manufacturers were working really on addressing this need with the plastic package, which is QMLV equivalent. But you can imagine if different manufacturers working on the same process, you will get maybe very different results, right? And those results are varying from each other, and that could be another challenge. And I'm thinking here about parameters like outgassing or any other environmental concerns. This was really not enough for space operators to be sure about the durability of the product. So Texas Instruments assembled a group of more than a dozen experts from industry and also standardization bodies to help developing this new QML Class P standard. And if you look now at this standard is fully accepted across the industry now, even ratified by European Space Agency now, so you can easily use it. And what does it mean for designers? For designers, this means it is very easy and straightforward to understand and select new parts because it's very similar to what they know from other applications. And also for space operators at the same time, it's very easy to accept new part, which means for them they can at the same time support more innovative designs using those packages.
That's great, because that's what we want to see across the industry. I think this is brilliant. And I don't know whether you guys agree, but from our position in the industry, I've always been of the opinion that the best standard at any level is the one that is actually used. And for you to say, the standard is being fully accepted across the industry, and as I mentioned, being developed from the supplier's point of view as opposed to top-down regulatory point of view, is great. And so, yeah, I'm glad to see that, as you say, is having a tangible impact on the industry by supporting those new innovations and designs, because you can quite easily swap out, reuse, and understand the parts that are in use and the reliability and performance of them. But you mentioned that you do still continue to support ceramics, the QMLV, I believe, standard systems. Could you elaborate on, maybe Michael, because Adrian just covered that, but could you elaborate on why you're taking this dual approach and what advantages or applications are better suited for ceramic packaging for space versus the others, the areas that we've talked about today?
Yeah, with all the excitement we share here on the QMLP and all the advantages we listed here, you might really think is like, why on earth would you still do the QMLV-RHA standard? There is good reason for it, right? There are still missions and systems that need this hermetically sealed devices. And as we stated before, right, the QMLP standard follows the requirements for low outgassing, but in the end, it's not no outgassing. And no outgassing is really needed for our optical missions, and is particular in the geostationary orbit, where you typically stay up there for way more than 10 years, possibly 15 years, and ideally even longer. And there is, of course, there's still the big need for having ceramic packages and avoid any outgassing at all, as that would cause layers on your optics and degrade your performance over time. So that's is definitely the systems that will keep driving for ceramics. But the other one, and that might be even more important, is the flight heritage. Flight heritage, as said, is a very important topic in our industry here. And now, if we would stop doing ceramics, we would probably obsolete quite a lot of existing products that our customers have successfully flown over time, and would also avoid that they could continue these things and give them facelifts or leverage all that investments over time. And of course, we will continue to supply QMLV. We will continue bring new devices out in QMLV, and we're definitely living up to our long-term supply commitment. So when it comes to the high-rel components, so there's very good reasons to continue with QMLV, and QMLP really comes on top of it.
As you mentioned, Michael, I think it's really allow Texas Instruments to extend our portfolio even further. So that's the point here. In addition to that's really an important step in giving our customers the very same experience they have on other market sectors, and we call it catalog product approach. And what does it mean for customers? This means it is easy to select. The part is really easy to select. This means you have the full specification, documentation, all the application notes, test results, even inventory levels and pricing information are available on ti.com. At the same time, it is very easy to design with those products. This means you have a strong technical support on our E2E forum or directly. You have all the samples and tools available directly from ti.com. So it's really with this catalog approach we are offering with this new standard. It's really a strong supply commitment to our customers for samples, even if they have a sudden increase in demand, but also for the long-term supply. And this means they can really predict the project execution and also the ramp up of the project. And this at the same time gives our customers a possibility to react to their end customers much faster, right? To the new missions or new projects, upcoming projects. So that's also very important, and it's helping our customers to allow them for the long-term growth, and also at the same time, because they have more time, they can focus on new designs. So if you think about this, the extension of the QML class V with this QML class P standard is really allowing a lot of innovation also for our customers.
Yeah, absolutely, which I think is a great way to look at this from a commercial perspective. And I think understand that this is an industry where these professional levels of service, of product availability, deliverability, and the ability to design with it is increasingly expected. And that there are more and more players looking at rapid production of technologies at all levels. How can we speed up missions? How can we speed up satellite development? How can we speed up subsystem innovation and testing? And I think the approach that you guys are taking on this is great. And I think that's a really good place to wrap up. We covered a whole lot about the in-depth importance of the packaging. Now, something that I didn't fully appreciate until we had this whole conversation today. And I think hopefully there'll be plenty of our listeners who will agree with that. Obviously, we will share plenty of links to ti.com and resources and TI's resources, previous podcasts that we've done with you guys on different topics, and all these different things that, as you say, in your product catalog approach, that engineers and mission designers and subsystem manufacturers and everybody in the supply chain need to really make the right decisions and run with the designs that they have while fully expecting the professional level of service, the reliability of the components, and being able to benefit from the technical innovations that you guys have discussed today for their own applications. So thank you both, Michael and Adrian. Fantastic to speak with you both again, and very grateful for you sharing the insights, as always, so openly about TI's work. Thank you. And thank you to all our listeners out there. Thank you both. Thank you all very much for spending time with us today, too, on the Space Industry Podcast. As mentioned, we will share further resources and information in the show notes that you can use based on today's discussion. And we would also be very grateful if you enjoyed this, that you would give us an honest rating and review on your favorite podcast streaming platform of choice, because it helps nudge those algorithms, share this information with more people. And please stay tuned until our next episode on the Space Industry Podcast. Thank you. Thank you for listening to this episode of The Space Industry by SatSearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.